In the previous section, we learned all about the data-driven graph modeling approach and how that can be useful if you have a pre-existing data set or you just want to get something going quickly. But now let's talk about a more formal approach using the graph data modeling framework. Getting started with graph data modeling is usually a pretty natural exercise. The drawings that you likely already have on your whiteboard tend to be great first drafts of your graph data model. You're likely already thinking about the objects that will become your vertices, as well as the connections that will become your edges. That said, for any substantial project, it'll still be helpful to have a methodology that you can use when designing your graph data models. Luckily for us, the traditional schema-designed data modeling framework is just as applicable to graph as it is other database types. Let's work through the process of defining our conceptual data model, our logical data model, and our physical data model in a graph example. We start by diagramming our conceptual data model in an entity relationship diagram. We draw all of our entity types, fill in the relationships between those entity types, and also assign all of our attributes. Notice that there's nothing graph-specific happening yet. We're simply filling in the entities and the relationships from our killer video application. Next, we map our conceptual data model onto our logical data model. What's great about this step is that when you're working with graph, the mapping is really simple and straightforward. Entities become vertex labels, relationships become edge labels, and attributes become properties on each of those. There are a few special considerations though, so let's talk about those. The entity type keys from your ER diagram will typically become user-defined vertex IDs of your vertex labels. Uniqueness is enforced automatically by DSE Graph, and the partitioning strategy is customizable. If you don't specify user-defined ID, then DSE Graph will create a system-generated ID for you. In this scenario, uniqueness is not enforced. So if you write two vertices that represent the same person, DSE Graph will happily obey and assign a unique ID to each of those vertices. This approach is not recommended and will be deprecated eventually. Another important thing to be aware of is that DSE Graph only supports directed edges, which means that symmetric relationships from your ER diagram will need to be arbitrarily modeled in a specific direction. I tell folks that if they aren't sure what direction the relationship should follow, they should just think naturally about the way they typically talk about their data and go with that. After all, the goal in all of this is to ensure that folks reading and writing the graph traversals see familiar patterns in terminology that they're used to. So if we take a look at this example, you can see that we have to make a decision about how to model the rated edge label. Now there's three options here, two that are good options and one that's not so good, and we'll talk about why. So as I said, you want to choose the option that's the most natural. So do we think of users rating movies, or do we think of movies being rated by users? In this case, I think it's more natural to think of users rated movie. So that would be my pick in this case. And as I mentioned, the third example, where you model it in both directions, that's not such a great choice. So what you want to do is choose the option that feels more natural and then simply modify your traversals so that they ignore the directionality of that edge label at traversal time. Similarly, bidirectional relationships will also need to be modeled in a single arbitrary direction. So for example, let's imagine that we have a nose edge label, and if I know you, you know me. We need to make a decision about what direction to model that edge. And just like the last example, you simply model the edge in a single arbitrary direction and then ignore that direction at traversal time. It's also perfectly reasonable to have cases where you will be storing multiple edges in multiple directions. For example, consider two users that like each other, but one user likes the other more than they are liked in return. You can see how that would be modeled here. Now let's look at how we can map our entity type hierarchies onto our graph model. We start with this simple and straightforward approach. But as you can see, it's not sufficient for capturing all of the necessary information. For example, in this case, it would be impossible to determine what role a person had when they were involved with a particular movie. Were they the actor or the director? We don't know. So perhaps we would consider doing a vertex-based mapping. But as you can see, this does become unnecessarily complex and would certainly result in some pretty ugly traversals. Here we see the property-based mapping approach, which is both simple and effective. The key thing to notice here is that we have used an edge property to describe the role a person held when they were involved with a particular movie. This approach is complete, and it could be the right choice in certain situations, but let's take a look at one more option. Here we're using edge-based mapping, which tends to be my favorite. We use edge labels to give meaning to the semantics of the relationship. A model like this will make it easy to write natural traversals that are self-describing and easy to maintain. After we work through the mapping for all of the elements from our ER diagram, we end up with a logical data model. And as you can see here in our example, our logical data model isn't that much different than the ER diagram we started with. That's a common thing that happens when working with graph. It also helps that the ER diagram is a graph itself. So the pictures you draw on your whiteboard tend to be a pretty good representation of what your logical data model will end up looking like. Finally, turning your logical data model into a physical data model is simply a matter of writing the necessary schema creation code. We're using the same approach here that you've likely become used to by now, where we define our property keys, then our vertex labels, then our edge labels, and finally, how those edge labels connect to our vertex labels. Lastly, the final step in our journey to complete our schema involves optimizing for performance. This is the step where you look at your data access patterns and determine how to construct your indexes and partitioning strategy to best serve those patterns. Now that you've learned all about the graph data modeling framework, go check out the exercise to give it a shot for yourself.